Okay, welcome back, nerds. I hope you all enjoyed your break. And if this is a future class that's watching this video and this is before the break, ignore that. Anyway, nerds, today, yeah, because this goes on YouTube, so yeah. Anyway, today we're going to begin learning some of my absolute favorite math. Logarithms! And I have a scared face. I didn't draw this. No, I did not draw this, but one of my students did. She's right over there. Anyway, this is a scared face. She's screaming, ah, because logarithms, da, da, da. Okay, now, how many of you had me as your Algebra 2 teacher? Yeah, I did. Well, in the past I have. So none of you raised your hand. Now, if this is a future video, and I was your Algebra 2 teacher, you're welcome. But anyway, for everyone in the room, I was not your Algebra 2 teacher. Now, show of hands, how many of you fully, deeply understand logarithms, what they do, and why they do them? One person raised a hand. I don't know about all that. We shall see. Now, let's be really clear here. Getting answers does not mean you understand what you're doing. I could teach a parrot how to say, Polly wants a cracker. But that doesn't mean the parrot understands English. Now, the reason why I asked how many of you had me as your Algebra 2 teacher is because if you did have me as your Algebra 2 teacher, then there's a really good chance your hand would have gone up when I said how many of you fully, deeply understand logarithms. I'm not casting shade. Our math department is fantastic. But I will say something that I mean in all honesty. When it comes to logarithms, I'm the best, baby. That's all there is to it. It's me. I'm the best. And you know why I'm the best? Because it's the first mathematics that I failed. It's the very first thing in mathematics that I failed. And it wasn't my teacher's fault. Mr. Bluebaum was my teacher. It was not his fault. It was because, due to family problems, I had to withdraw from the school and go to a different county for a couple months. And while I was in a different county, I went to a school that was not on block scheduling like we were here. And when I came back, I had missed the entire exponential functions and logarithm functions unit. And then I had to try to teach it to myself. And if you almost remember logarithms, you can, pretty much know exactly how that went. I failed miserably. This was me. I failed miserably. And that F test led to the first C of my life, Q1, freshman year of high school, Algebra 2 honors. However, because, and again, I'm going to toot this horn, boop, boop, I am so good at mathematics, and because Mr. Bluebaum is a great teacher, I managed to get an A, Q2, so overall I got a B for Algebra 2 honors, because block scheduling class only lasts half a year, okay? But it was the first mathematics that I failed. This was me every time I saw logarithms. Every time. And I mean, I graduated college with a degree in mathematics. And this was me every time I saw logarithms. Now, I could get answers, but I knew deep down. Okay, well, a more manly me, if you can imagine. But anyway, I knew deep, yeah, put a mustache on her. There we go. Well, yes. Anyway, I knew deep down I didn't understand answers I was getting. And I knew they were right, but I didn't understand. I worked for a tutoring company in college, tutoring college students in mathematics. And I was teaching them how to get answers. But this is how I felt, because I was petrified they were going to ask me why. Because if they had asked me why, it would have been really, really difficult for me to explain. I have good news, though. This is no longer me. I'm going to draw a much more accurate representation of me. There, much more accurate, okay? I love logarithms. Love them. They're some of my absolute favorite material to work with and to teach, because I know them so well. I made them my job because I don't like being beaten by mathematics, and I felt like logarithms had beaten me. And because of that, I teach them in a slightly different way than anybody else does. In fact, it's going to even make the order of these notes be weird. But trust me when I say, if you pay attention and try to understand what it is that I'm saying and doing, logarithms will not be frightening. Okay? All right, here we go. Why are logarithms difficult for people to understand? Because when your teacher introduced it, it looked like magic. They used tricks to show you how to get answers and never explained to you why that works and what that means. For example, I'm sure you all saw questions like this. Write the exponential form as a logarithm. The very first thing you were taught how to do was to convert between forms. And you probably had some kind of little cutesy trick for it, and maybe an arrow was drawn somewhere. You used tricks to figure out how to get answers and never understood what they meant. And then you tried to build a house on top of that foundation. And then as soon as you got out of it, you're like, thank God I'll never see logarithms again. And then forgot it all. Jokes, here they be. But I'm going to get you from shim to here, okay? Yes, she, him, shim, okay? All right. Here it is. Allow me to introduce to you a brand new symbol. You have never seen this symbol before. And I'm not going to tell you what this symbol does. I'm going to ask you to tell me what the symbol does. Okay? Just go with me on this. We'll just scoot that distraction out of the frame. Ready? Psst, pay attention. I'm thinking the order I want to write this. Not multiplication. You shut up back there. Okay. If I asked you to solve for x, please tell me what operation you would use. Square root. And you would use this operation on both sides of the equation, correct? And the reason why you use square root is because square root is the inverse of exponent of 2, correct? In fact, not only would you write a radical, more specifically, you would use the correct index, because a third root is not going to cancel a square, and a square does not cancel a third root. You need the index and the exponent to match. And you understand through the mathematics that you've learned inherently that if the index matches, you have isolated the x, correct? Okay. I don't care about answers. I don't care. I know the answer too, okay? I'm going to use a symbol that I created. No joke, I created this. Tell me what that symbol does.
Oh, it's like the square root but for the bottom, for the base.
So you're telling me it cancels the base? Like this? Makes sense, right? I mean, above canceled the matching thing, below canceled the matching thing, right? Hey, look, x is alone, right? So I could write this. But I have used an algebraic idea, and that is an inverse operation to get the x alone, did I not? Guess what that symbol is? More specific than logarithm. It's log base 2. You see, logarithm is an operation. And the reason why a lot of people struggle with understanding what it is and how it works is because they're on their phones while I'm teaching, is because logarithm is a word. in our language. Log is a word in our language. So if someone says, log base 2 of 8, they heard words. They didn't recognize it as a symbol that was performing a job on a number. What is the value of a division symbol? What is the value of a square root bar? The reason why you're thinking that I'm high right now is because those questions don't make sense, right? Symbols don't hold value. You can't divide by a square root bar, right? Well, guess what? Log base is an operation, like plus or minus or square root. It itself is not a number. It does not hold value. It does a job to things. And its job is to cancel an exponential base. And it only cancels it if it matches. So the answer here is 3. But the reason why I know 2 to the third is 8. But the reason why it's 3 is because 8 could have been written as a number with a matching base. And when the bases match, just like when these two things match, they cancel. And you're left with a numeric value. Log base b, meaning any base I want, is a symbol. It has a job to do, just like a square root bar has a job to do. Its job is to affect the numbers that are within it. Now, talking about its job, if I said to you, what's the square root of 9? We all know the answer is 3, but why is the answer 3? The answer is 3 because you understood the set of instructions that this symbol gave you. This set of instructions said, find the number that when multiplied to itself 2 times gets you this. Find the number when multiplied to itself 4 times gets you this. You understand the set of instructions for a radical bar. So one of the issues with a logarithm is that you didn't understand the set of instructions. The set of instructions for this symbol say, what power of 2 gets me this number? Whereas this says, what number multiplied to itself this many times gets me this number. This says, what power of 2 gets me this number. So if it says log base 2 of 16, your answer would be what? 4. Because it says, what power of 2 gets me 16? The fourth power of 2 is 16. And if I said to you, what power of 2 gets me a 5? Well, the answer is it's not a whole number, is it? And we don't know what that number is. But we could estimate. We could estimate. We could say that I know 2 to the 2 is a little bit smaller than 5, right? So that means this answer is bigger than 2. I don't know what it is. It's like 2.1 or 2.01, something like that. But the point is, I have a general understanding of what it's asking. It's asking me, what would I have to raise a power of, what would I have to raise 2 to the power of to get close to 5? And because 5 cannot be written as a base 2 number without using logarithms, my answer can't be written without using logarithms. Just like if I said to you, what's the square root of 6? You would not be able to give me a whole number answer because no number multiplied to itself 2 times gets you 6, except for the square root of 6. So this is the best way of representing that value, and this is the best way of representing this value. There's just not a better way because it's irrational. Because it's irrational. So because they're irrational, the best way to write them is using their symbols. And because this symbol couldn't do its job on this number, I couldn't do anything with it. And because this symbol can't do its job, and this, log base 2 of parentheses, is the symbol. It's a symbol. It has no value. It has a job. Cancel exponential base 2. So, you know, if I wanted to use algebra to get rid of that base 3, I would have to use the appropriate inverse operation. And I would have to use it on both sides of the equation. It's algebra. So what cancels exponential bases? Log of the matching base. So if I want to cancel exponential base 3, I use log base 3. I just use log base 3 on both sides. And lucky for us, 27 is a number that is also base 3, which means I can get a pretty answer. If it said 25, I would have a logarithmic answer, because 25 is not a number that can be written as a power of 3. Cool with that idea? They're not magic. They're algebra. They are an inverse operation. They cancel another operation. You just weren't used to thinking of an exponential base as being an operation, but it is. In Algebra 1, if you can think back that far, you were taught to solve this kind of thing by making the bases match on both sides. And then all you did was set the exponents equal to each other and you were done, because the bases matched. But that, ladies and gentlemen, is not algebra. That's magic. It's a magic of equivalent statements. But I ask you, what algebra removed the base 3's? The answer is log base 3 of both sides did. You used log base 3 on both sides. It canceled both these exponential base 3's and left you with your answer. Always interrupted. So back to the grind. Anyway, something else that we need to talk about. A couple other things we need to talk about. So log base of stuff and exponential base of stuff only cancel each other when the bases match. But because they are inverse operations, the order that they work on each other doesn't matter. So if I said to you, to isolate x, you would be attempting to get rid of the log base 2, which is an operation. So you would use its inverse operation, which would be exponential base 2. So what you would do is you would use exponential base 2 on both sides of the equal sign. Sorry, there was a 5 over there. On the left side, the exponential base 2 and the log base 2 cancel each other out. And that leaves you with x equals 2 to the 5th, which is 32. Now something very interesting just happened here. And you know what? It was also happening here. I had a number that was sitting in the exponent position, and now it's no longer in the exponent position. Now, I'm going to leave this on the video, but the image on the screen isn't going to change. There should be sound, though. There's going to be sound, because I'm going to keep talking. So over here, I have a stool. And we're going to let this stool represent an exponential base of some sort. Now on the top of the stool, I've got this nice tiny bottle of glue. And I chose something small because, well, exponents, superscripts are usually written kind of small, right? And I'm going to put it right here on this stool. Boop. You see, what a logarithm does is, as long as the base of the logarithm matches the exponential base, the logarithm can come through and kick the stool out from underneath of the glue. Now, what happened to that bottle of glue when the log came through? What did it do? It fell down. And it is now just a number sitting on the ground, which is exactly what you saw happen here and here. They fall down. They're no longer exponents. They come down as values. They've simply been isolated. Okay? And I don't think you'll forget me kicking a stool over And I know the substitute teacher underneath me will not forget the sound of it today either. That's the second time that they've heard it, because I did it in period 2 as well. I do it every year. I'm sure Minnie is sick of hearing that sound. I do it every year. You know, it's funny. I have to teach it to the Algebra 2 kids later this year too. So it'll happen again. And I teach that class 3 times a day. So she's going to hear the stool 3 times that day. It's going to be good time. Alrighty, I think, so what else do I need to bring up before we get to the actual notes? Special kinds of logarithms. Did I describe to you what this says? It says what power of base gets me this number? Okay, good. All right, so in our number system, one of the very first things that you're taught early on in mathematics is to identify place values, right? You go, oh, this is the tens place, the hundreds place, thousands. No, wait, I can do this. Ones, tens, hundreds, thousands, 10,000s, and even as the decimals, tenths, hundredths, thousandths, so on and so forth. The reason why we use those kinds of words is because all of those things are powers of 10. 10 to the 1s, 10 to the 2s, 10 to the 3s, 10 to the 4s, 10 to the 5s, 10 to the negative 1s, 10 to the negative 2s, 10 to the negative 3s. Our number system is base 10. Every single number in our number system can be written as a power of 10. And because of that, mathematicians ended up writing that a lot. Log base 10 of happens often because our entire number system is base 10. It happens so often that they were like, hey guys, can we, and I'm assuming there was a gal every now and then doing math, can we all agree that since it is the most common one, that we could just be lazy and write log, and we all just kind of know that it's base 10? I mean, we've already done it for the square roots. Why can't we do it for the logarithms also and just be like, look, you know, we're tired of writing that number. It's too common. So they did. And this is called the common log. There is a log button on your calculator right there. You'll notice it does not have it doesn't have a base. That's because it's base 10. Hey, look at the blue symbol right above it. 10 to the power of the inverse operation. So the common log, we don't write the base, but the base is 10. The base is 10, okay? There's another extremely common logarithm. It comes up a lot in mathematics, but specifically it comes up a lot in financial mathematics. It also happens a lot in complex number mathematics, but let's not worry about that right now. And that is this logarithm. Base E. Because E's show up a lot in higher mathematics. A lot. So we end up doing a lot of log base E's. So much so that the mathematicians are like, oh my gosh, I'm so tired of writing log E. Because, to be real with you, we want to save space. We want to write less things. Mathematicians are the ultimate lazy, okay? We're trying to do less and less writing of things. So because of that, they got real lazy and stopped saying log base E. And what they said was, well, since E is known as the natural base, this is literally log of the natural base. Let's just say Ln, which literally stands for log of natural base. Ln is not different mathematics. It's lazy. That's all it is. It's lazy. It's an acronym, like NASA or SCUBA. It's an acronym. It says log of natural base. It's the same thing as saying log base E. So whereas log base 10 cancels exponential base 10 and log base 2 cancels exponential base 2, log base E is Ln. So Ln cancels exponential base E. It's a highly specific logarithm. The N stands for natural base. Log of natural base. It is log base E. Cool with that? Great. Couple rules. Of logarithms. These rules come from the rules of exponentials. If I said b to the x, this is an exponential. You guys remember any of the rules for that base? The base can't be negative. Okay. Because the base can't be negative, there would be no way for the negative base logarithm to exist either. Because remember what logarithms do, they cancel exponential bases. So since no negative based exponential base exists, no negative base logarithm exists either. And if you tried, the answer would just be undefined. You can't do that. There's one more rule about the base of an exponential. See if anybody can remember that one. Why are there two different kinds of exponentials? Why is there a growth and a decay? Where does the change occur? Right, but what value of the exponent is the change? The deciding factor between growth and decay? B can't be 1. It could be between 0 and 1. It could be greater than 1. But the base cannot be 1, because if it was, you'd say 1 to any power, and it doesn't matter what you say, you would always get 1 back. That's not an exponential. And because of the fact that there is no base 1 exponential function, there is no base 1 logarithm function either. It's the exact same rules. Because, well, they do basically the same thing, just in reverse order. Yeah? Okay. Great. So here's some log crap going on. This and this are very important logarithms. Log base b of 1, regardless of what the base is equal to 0. But the reason why is because what this says is, what power of b would get me a 1? B to the 0 would get me a 1. So this logarithm has a value of 0. What power of b gets me a b? The first power does, because b to the first is b. What you see here is log base b doing its job, canceling exponential base b, and the y falling down to the ground. See it? Yeah, like that. And here you see the exact same property, but in reverse order. You see exponential base b canceling log base b, yeah, letting the x fall down. These are the exact same rules, but they're all base e instead of base b. What power of e gets me a 1? The 0 power of e. What power of e gets me an e? The first power of e. Log base e and exponential base e cancel each other. And exponential base e and log base e cancel each other. There you go. Remember, ln is just a highly specific version of a logarithm. Highly specific. Okay? So, oh, and you know what? I forgot to say one thing. It's vocabulary. I will use the vocabulary often. When you set up your logarithms, they should always have parentheses. And when they don't, the assumption is that they are there. Okay? So, if I wrote log x plus 1, this is like that. The thing next to the logarithm is always going to be inside the logarithm. It's what the logarithm is working on. You want that plus 1 to be inside the logarithm, then it had better be inside the parentheses. Okay? Okay. Now let's talk about this whole inside the logarithm, the stuff it's working on. There's a name for the stuff that is getting worked on by symbols in mathematics. For square roots, we say it's radicand. But that's only for, well, all radicals. That's only for radicals. But I could still use another kind of word that describes the inside of a function. The inside of a function is known as the argument. So we would say this is the argument of the logarithm, the argument of the radical. And when we get to it, the argument of the trigonometry. In mathematics, the argument means the stuff that's being worked on by our function. That's what that means, okay? So, like here, the argument is 8, the argument is square root 3, the argument is 1 over 25, so on and so forth. So here we have a bunch of true statements, but we want to say why they're true. Log base 2 of 8 equals 3 for a very specific reason. And it's because 8 could have been written as 2 to the third. And because 8 could have been written as 2 to the third, my logarithm could have said log base 2 of, and instead of saying 8, I could have said 2 to the third. And this would have allowed the logarithm to do its job. That's why it equals 3. I hope you see that nothing I've done is magic. All I've done is introduced a symbol and told you what it cancels. It's an inverse operation in mathematics. That's all it is. We are just unfortunate that we speak English, because in English, log is a word. Log is not a word in Spanish, but they still write log when they're doing mathematics. And they recognize it as a symbol, not a word. In English, it happens to be a word, which is confusing. So why does log base 3 of square root 3 equal 1/2? Because square roots are exponents. So my logarithm could have been written like this. And if it had been written like that, then the logarithm could have done its job. I'm a mathematician, not a magician. I don't do magic. This is algebra. And I think you get what's happening here. 1 over 25, this one I'll do in 2 steps. 1 over 25 could have been written as 1 over 5 squared. But sometimes it's convenient to take things out of the bottom of a fraction and move them to the top and just make the exponents negative. I'm not going to write this stuff on the side again. But this is why your answer is -2. Because what power of 5 gets me a 1 over 25? So really the question's easy. You say, well, what power of 5 gets you a 25? 2. So what power of 5 gets you a 1 over 25? Oh, -2. You see? The negative flips it upside down. Uh-oh. There's no base written. The base isn't written, so what is the base? 10. This is the common log. We don't have to write it. So the reason why log of 10 equals 1 is because 10 could be written as 10 to the first power. And then the log base 10 cancels the exponential base 10, leaving just the 1. And this question, I'm just going to write it in words. Why does this work? Because exponential base 6 and log base 6 are inverse operations. I mean, so you could literally just do this. Whee! Just like that. So, Algebra 2, taking you back to Algebra 2. I know for a fact, since I wasn't your Algebra 2 teacher, the very first thing you learned how to do was to convert exponentials to logarithms and then logarithms to exponentials. I know that's what you learned. That's what everybody teaches for some strange reason, except for me. I don't teach it that way because that's magic. That's trickery. Instead, what I would say is, let's write this in an equivalent format. And you might be thinking, why would I bother writing anything in an equivalent format? I mean, well, I can tell you, you've done it a lot in mathematics. Let me prove it to you. It's the same knowledge, written in a different format. How about this? Can we agree that both of these give you the exact same information, just in different formats? You've done this plenty of times in mathematics. You've done this plenty of times using inverse operations, right? Okay, we're doing the exact same thing, only with exponentials and logarithms. So I'm not going to be doing any of this writing it or converting. No, I don't do that. What I do is I use algebra to get it to the format I want. I want logarithmic format. That means I'm going to use logarithms. I have an exponential base 4. What cancels it? Come on, somebody say it. What cancels exponential base 4? Log base 4. So what I'm going to do is perform the operation log base 4 on both sides of the equation. In here I had a 4 cubed, and over here I had a 64. On the left side, log base 4 can cancel exponential base 4, and what we're left with is a true statement that is not in exponential format. It's in logarithmic format, but it's the exact same information. You're looking at that and you're thinking, whatever, I'm just going to use a shortcut. And I'm thinking, whatever, I'm just not going to feel bad for you if you don't understand. Okay? Because I'm telling you, I don't use tricks. This is algebra. I taught a college student an entire chapter of logarithms in 30 minutes when I tutored for SCF. And he asked me, why didn't my professor teach it this way? And they said, because she doesn't understand logarithms. Oh, she's smarter than me. I worked with her. She used to work at Northport High for a very short amount of time. She was there 1 year. She's smart, but she doesn't understand logarithms, not like I do. That's all there is to it. This one, I want to write it in logarithmic format. That means I don't want an exponential. That means I need the exponential base 9 to go away. So how am I going to get rid of an exponential base 9, everybody? Everybody typically means all people. So log base 9 would have been great to hear from all 23 of you. That would have been awesome. But anyway, I'm going to use log base 9 on both sides of this equation. Because I am really trying to drive home what they are and what they do and why they do it. I'm not interested in what the answer is. I'm interested in why the answer is. These are not any different. And because of that, I'm just going to not do them. I mean, the answer is, I'm hoping you can see that it's -5 equals log base 2 of 1 over 32, and 1/2 equals log base 64 of 8. They are not different. Okay? They're exactly the same. Nothing special. I don't see a reason to do 3 and 4 versions of the exact same question if they're not going to show me something new. So we'll flip it over, and we'll get to the other thing that I wanted to do, and that is running our logarithms in exponential format. Again, I'm not going to use any trickery, and I'm not going to talk about convert. What I'm going to do is I'm going to use algebra, and I'm going to say, if I want an exponential, that means I need the logarithm to go away. So how am I going to make a log base 5 go away? The answer is with an appropriate exponential base 5. You need the bases to match. So the operation here is exponential base 5 on both sides. You write both sides of the equation as exponents above base 5. On the left side, the exponential base 5 and the log base 5 will cancel each other. Because they're inverse operations, the order of that does not matter. And same thing here. If I want an exponential, then I need the logarithm to go away. I then have to cancel a log base 625. You cancel log base 625 with the appropriate exponential. Exponential base 625. You write the previous equation as exponents above your new exponential base. The log base and exponential base will cancel each other because they match. They only cancel when they match. Leaving us with 5 is 625 raised to the 1/4. And then just like the front, these are not any different. You would use exponential base 1/2 on both sides. You get 64 equals 1/2 to the -6. You'd use exponential base 2 on both sides. You get 1/32 equals 2 to the -5. It's not new math. And it's not magic. So where'd she go? Give me this girlie. No. She's not allowed to be frightened anymore. Because she's a power nerd now. Woo!